Welcome to the lecture on welding distortion. So, in this lecture we are going to discuss about the different type of distortions which take place in welding. So, we know that there are formation of residual stresses, development of residual stresses during the welding process, and if the residual stresses values are more than a limit, more than the yield strength of the material, or you have the restraint on the sides and the formation of residual stresses, and there is hindered expansion and contraction, then that may lead to the distortion of the welded specimen. So, depending upon the structure or depending upon the type of specimen you are welding, you will have different types of distortion in the welded specimen. When we are welding in a certain direction, there may be there may be distortion in that direction, or it may be in the transverse direction, depending upon even the sheets, if it is thinner or thicker. So, or it may sometimes bow down, or it may be a rotational type of distortion, it may come closer or it may go apart. So, depending upon that, you will have different types of distortions that we will discuss in this lecture. So, what is distortion basically? Any unwanted physical change in a welded structure is called distortions. Means anything which is going out of shape, which is not in the shape for which it is meant to be, then it is said to be distorted. So, usefulness of the component may be affected. So, when any material becomes distorted, when anything will be out of shape, then its usefulness will be affected. The purpose for which it is going to be used, it will be affected. Suppose you have, so dimensional changes will be occurring, and then the purpose for which it has to be used, or it has to be used in a proper place or in a proper shape, that is basically gone. So, that way its usefulness may be gone, either it will be devalued or it has to be rejected. So, if it is devalued, it's a loss of the productivity. Maybe many a times you are trying to rectify that component, so you will have the added cost required to rectify the component. So, that how you are going to suffer in economic terms. And maybe that it is rejected. So, in that case you have to further go for the fabrication process. So, that is again a loss. So, that way this is going to reduce the productivity of the organization. Distortion is caused by non-uniform expansion and contraction of the weld metal and adjacent base metal during heating and cooling cycle. So, we have already studied about it, that when you have uneven cooling and heating, so that you have the cycle to which this material is subjected to. So, during that the stresses will be generated, and then because of that there may be the distortion because of this non-uniform expansion and contraction of the weld metal and the adjacent base metal. We have already studied that how in the adjacent metal, when you are welding in the middle portion, then this tries to expand and the adjacent portion will try to contract it. Similarly, while cooling, it will try to contract and the adjacent metal will try to further let it be expanded. So, this way you have the cycle under which it is subjected to the either compressive or tensile stresses, and then ultimately you have the formation of certain type of stresses in the material. So, that way, because of this heating and cooling cycle, you have the formation of stresses at the different points at any section, and that leads to the distortion of the specimen. Now, we have to understand that what are the different factors which affect the distortion in the welds. So, you have the factors that can be categorized under either the material properties or the welding processes and procedures. So, the materials which we are basically using for welding process, they have its own specific properties, and as these properties vary from material to material, so the expansion characteristics or the distortion characteristics will also be changing. So, the properties which are primarily important for deciding such kind of distortion is, one is the coefficient of thermal expansion. So, if the coefficient of thermal expansion is more, in that case as the temperature changes, in that case the expansion or contraction will be more. So, in that case, once that is more, then it means the distortion will be more. So, the material with lower value of thermal expansion will be more prone to getting distorted than as compared to those material which have very high coefficient of thermal expansion. So, that is basically a function of the change in temperature. So, that is why this coefficient of thermal expansion is one of the important property of the material, because of which this distortion is affected. Thermal conductivity. Now, we know that because of the thermal conductivity, the heat which is pointed at one point, that heat has to dissipate. Now, the heat which has to dissipate, how quickly that is dissipated. So, whether it is dissipated quickly or whether it is dissipated slowly. Now, the thing is that when the heat will be dissipated quickly, means you have high thermal conductivity. So, if the thermal conductivity is higher, in that case you will have temperature gradient lower, and if the thermal conductivity is lower, you will have high thermal gradient, because what happens that if so you have this is the welding. So, here once you are heating at this point, now the heat has to extract from here and from here. Now, if the thermal conductivity is high, it will quickly pass through it and then it will go to the surroundings. So, and otherwise the heat will be contained for more time into this zone or into this zone or even in this zone. Now, if that is there, in that case you will have more chances of the distortion. So, for basically higher thermal conductivity, you will have lower distortion, and for lower conductivity you will have high thermal gradient and you will have high chances of distortion. Then comes the yield strength. Now, if the yield strength value is higher, in that case the residual stresses values are higher, and in that case the distortion is also likely to be higher. Similarly, the modulus of elasticity, or which is the property that is rigidity. So, if that is more, in that case it will resist any kind of deformation. So, for a material with large value of modulus of elasticity will be likely to undergo less distortion. So, that is how these properties affect the distortion in the welds. Coming to the welding processes and procedures. So, for a given design, so you have the deformation which will be determined by the order of assembly of the components. So, how you are doing the assembly. Then you will have the welding current and voltage, and similarly you have welding sequence, and you have the clamping methods. All these things are important. Now, the amount of weld metal. So, when we talk about the amount of weld metal, amount of the distortion will be depending upon the volume of the weld metal. So, now again the volume of the weld metal which is heated, it will be depending upon the welding processes, like you have what is the welding speed, what will be heat input rate and all that. So, if the amount of weld metal will be larger, certainly it will be giving you more and more distortion. So, and then welding speed is there. So, welding speed is there, edge preparation, fit up, and then and the welding procedure, all these things are basically important factors in distortion. So, when we talk about the welding process, in that case we have to be sure that of certain concepts, like either we can have a source which is giving the concentrated heat source, or it is not concentrated heat source. So, it may have a very dispersed type of heat source. So, whenever you are using the concentrated heat source, it is going to create less amount of distortion, because as we have studied the welding metallurgy part. So, when we use the concentrated heat sources, in those cases the zone which is affected because of the heat also is smaller. So, when we use the concentrated heat sources, they give lesser distortion than the those type of processes which have the spread heat sources. Like if you take the example of electron beam welding or TIG welding or so, or even TIG welding if you take, and as compared to the flame welding. So, in the case of flame welding, oxy flame welding or so, you will have a large amount of spread. If you take the electron beam welding, which is just like in a beam shape, it goes and does the welding operation. So, in that case, in the case of EVW electron beam welding, you will have lesser amount of distortion as compared to the flame welding. So, that is why the concentrated heat source is preferred than the spread type of heat source. Similarly, the welding speed is also very important. Welding speeds, if it is higher, then it will be giving the lesser distortion, because if the speed is higher, then the spread will be smaller. And in that case, when the spread is smaller, then the distortion will be smaller. So, this way the distortion is affected. Then the penetration. So, if you talk about the penetration, then the penetration if the penetration is deep, so deeper penetration will give you less distortion. Deeper penetration gives less distortion, maybe because of the fact that it will hold the plates with more strength, and then so the distortion, chances of distortion will be lesser in the case of distortion. So, you have deeper penetration that will be leading to the less distortion. Similarly, pass. So, the single pass will give you less distortion than multiple pass. So, as you increase the number of passes, the chances of distortion will be more. So, the single pass will give you less distortion than the multiple pass. As we discussed that the weld metal also should be minimum, because amount of weld metal being higher, that will lead to the larger value of stresses, and then so the larger distortion chances in that case. We also talked about the edge preparation and fit up. So, we must have a proper edge preparation. So, as we discussed that we should ensure that there should be minimum amount of weld metal, and you must have the edge preparation. While we do, it should be as uniform as possible, so that you have consistency as far as the shrinkage is concerned. So, along the joint if there is shrinkage occurring, then if this is uniform, then there will be consistent shrinkage. So, that will lead to lesser amount of accumulation of these stresses. Now, also that when you have close fit up of the joint, in that case also it will reduce the stresses. So, it will be reducing the, if you have the fit up, if close fit up is not there, then the more amount of weld pool weld metal will be there in that zone. So, that will further lead to the increase in the stress value. So, this close fit up also is necessary for decreasing the value of the residual stresses. Now, talking about the procedures, so we talked about the welding processes and parameters, and other procedures if you talk about. So, we should try to go for mechanized type of welding. So, that will give you the less distortion as compared to non-mechanized ones, and you go for single speed, single pass, high speed type of welding should be preferred, which will be likely to give you the less distortion as compared to the other type of joints where you have multi-pass, low speed kind of welding processes. Also, as we discussed in our last lecture, that we should also use the processes like skip welding and backstep type of welding process to reduce that distortion. So, that is another way by which we see that the stresses are smaller. Now, coming to the longitudinal types of distortion. So, when we talk about the distortions, then we must know that what are the types of distortion, how the distortion looks like. Okay. So, distortion is normally of these types, like you have longitudinal shrinkage, you have transverse shrinkage, you have angular distortion, you have longitudinal distortion, you have rotational distortion, and buckling and twisting. So, we will discuss one by one about all these type of distortions which take place in the case of welding. So, coming to the longitudinal shrinkage, as you see, this is the example of longitudinal shrinkage. So, as you see that this is the longitudinal direction. So, in this case the material shrinks, and you see that there is a void which is formed at this point. So, this shrinkage which is occurring in the longitudinal direction, that is known as the longitudinal shrinkage, and that basically makes the shape, that at this place this shape becomes like this. It would have been flat in ideal case, but because of this shrinkage it shrinks in this direction, in the longitudinal direction, and that is why this is known as the longitudinal shrinkage. So, normally about 1/1000th of the weld length is the normal value of this longitudinal shrinkage, and it is quite less, very less as compared to the transverse shrinkage, and there are certain formulas. So, basically depending upon the current and the length of the weld, this longitudinal shrinkage varies. Also the thickness of the plate. So, if the thickness of the plate will be more, in that case the longitudinal shrinkage will be smaller, and current and the length of the plate being length of the weld being more, the longitudinal shrinkage will be more. So, there is a correlation between this longitudinal shrinkage and these operating parameters for a certain type of butt weld. So, for butt welds, as we see here, for that normally that is how it varies. Similarly, you will have certain fillet welds also. In the case of fillet welds, you will have you have the areas that is straining cross section, and then you have the weld metal cross section. Based on that, this longitudinal shrinkage will vary. So, that way it varies. So, it will be transverse, this longitudinal shrinkage for fillet weld, it will be directly proportional to the weld metal cross section. So, if it is more, in that case the longitudinal shrinkage will be more, and the restraining area, if it is resisting cross section is, if it is more, in that case the longitudinal shrinkage will be less in the case of fillet welds. So, that is how you calculate the longitudinal shrinkage in the case of butt and fillet welds. Now, coming to the transverse shrinkage. So, as we discussed that when the shrinkage is in the direction of the welding in the longitudinal direction, then it is the longitudinal shrinkage, and when the shrinkage is in the transverse direction. So, because you have the solidified metal here, so there will be shrinkage also in this direction, and that so as you see here, this is the butt weld, and you have the shrinkage in this direction. So, because of that the actual size should have been here, the dotted line, but the actual size after the shrinkage the line appears like this one, which is the bold line. So, this appears, this is the example of the transverse shrinkage. Now, the transverse shrinkage, as we know that again it depends upon the cross sectional area of the weld. So, if it is more, in that case the transverse shrinkage will be more, and if the weld thickness is more, then transverse thickness will be shrinkage will be less. So, the major factors which are causing this non-uniform transverse shrinkage, they are the rotational distortion and the constraints. So, because of that these transverse shrinkage are affected. So, these are the longitudinal as well as the transverse shrinkages. Next is the longitudinal distortion. So, in the longitudinal distortion, as you see, this is how the material will look like. This is the example of longitudinal distortion. So, that is also, so as we see, this is your longitudinal distortion, which is nothing but bowing or and bending also. So, now in this case what we see is that the weld line, it will be not coinciding with the neutral axis of the welded structure. So, if it does not coincide with this neutral axis of the welded structure, then we say that it is a case of longitudinal bending. So, it may be bowing or twisting. So, you can see it is bowing or bending. Then again you have here what happens that you can calculate the amount of these longitudinal bending, and normally it will be depending upon the cross sectional area of the weld, then distance from the CG to outermost fiber. So, that is another parameter. Then you have the length of the weld and also the moment of inertia of the structure. So, based on these parameters we normally calculate these longitudinal distortion of the welded structure, and we calculate these values in terms of some numeric values. So, this way longitudinal distortion is calculated. Next type of distortion, you have the rotational distortion, as you see here. This is the example of rotational distortion. Now, this is observed at ahead of the point of the welding, and when you are welding the sheets, then many a times you see that these sheets, when you are doing the butt welding of the sheets, then they come either closer to each other or they are basically the distance between them is widened. So, in this case what you see is these two edges, either they are coming closer or in this case they are going away. So, this is the example of rotational distortion, and in this case because what happens that you have there is a limit of the rate at which the heat has to be conducted. So, because of that, you know, either this seat in some cases either it comes closer or it comes, you know, depending upon the welding speed also it matters. So, the way you go, you may go fast or you may go slow. So, based on that and depending upon the heat input also, that way you have the either these two sides. So, many a times when you are doing the larger you know sections, larger plate which you are welding, and if you are not putting the tack welds, you can see that if you are doing welding, maybe that when you reach towards the end, either they are separated apart or they may go like this. So, you have to again pull it and then do the welding. So, that is the example of the rotational distortion. So, this is about the rotational distortion. Then comes the angular distortion. So, this is what you see. This is the kind of angular distortion. So, this occurs at butt, lap or T joint and even on the uniform joint or cruciform joints. And this is about because of the symmetrical double sided welding, this type of distortion occurs. You see that you have the symmetrical double sided welding that creates such kind of angular distortion. As you see, it comes in that shape like this. Now, how much this angular distortion will take place, that will be depending upon the width and depth of the fusion joint, fusion zone, and relative to the plate thickness. So, as compared to the plate thickness, how much is the width and depth of the fusion zone, and then which type of joint it is, and what is the weld pass sequence. So, then thermomechanical properties of the material, and you know, welding processes, all these are the processing parameters which affect the amount of angular distortion that the material will be subjected to. Like the parameters of welding process, then again comes like heat input, you know, per unit length of weld, and distribution of the heat source density. So, these are the parameters which affect this extent of this angular distortion or the amount of the angular distortion to which it will be subjected to. Then comes the buckling and twisting. As you see here, this is the defect which is known as the buckling and twisting. So, in this kind of you know, this is when you are welding the thin plates, then this kind of defects are likely to occur. Now, what happens that there will be considerable amount of residual stresses which will be developed in the areas away from weld, and then that causes welding. So, in the case of when we are doing the welding of thin sheets, and we have seen that if you recall, when we use the sheets welding using the DC welding, and if you use the electrode with you know, reverse polarity, that is or straight polarity, in that case your work is positive, reverse polarity the work is negative. So, when you use a straight polarity for thin plates, in that case that will be heated, and in that case when you do the welding, so these more likely these plates are subjected, these thin sheets are subjected to that type of distortion. So, in those cases they cause this buckling of these sheets. So, buckling occurs, basically buckling or twisting you can say. So, buckling occurs when you know, specimen length will be exceeding the critical length for a given thickness. So, in those cases when you do the welding, that time distortion which occurs, that is known as the buckling. So, with related to this bending, if you talk, you try to compare to the bending distortion, you will have more than one you know stable deformed shape in that case, and amount of deformation in buckling distortion is much more you know, as compared to the bending. So, that is the basic difference between this buckling and bending distortion. So, these are typically the different kinds of the distortion which occur in the case of welded structures. These are the normally 6 types of distortion which occur in the case of welded structures. And you can compute the values of these distortions using the standard formulas which are available, and the purpose is that once you know the different kinds of distortion, and once you are knowing that what are the root cause of having these distortions, then you can have the accordingly the proper ways to tackle these distortions and lowering the value of the distortions. So, we will study about those methods, how to control the distortions in weldments in the coming lectures. Thank you very much.